Hello, dear students. This is our online lecture number 5. Remember before we covered in chapter 4, this is chapter 5. Remember we covered in chapter 4 earlier the case of having one variable input in addition to a number of fixed inputs, and the individual producer was producing one output only. Okay? And then in that chapter 4, we talked about how much I should use of that variable input in order to maximize my net returns. And we obtained the optimality condition that claims to say use the level of the variable input at which the value of marginal product of the variable input is equal to the unit price of the variable input if you want to maximize your net returns. And remember, we distinguish between net returns and profits, and we said that net returns is equal to total revenue minus total variable cost. Profit is equal to total revenue minus total cost. And remember the different names we assigned for total revenue. It is total revenue, total receipts, total value product, and the total returns. After that, we, again, in the context of talking about having one variable input in addition to a number of fixed inputs and producing one output only, we also showed what the optimality condition of how much the individual producer should produce if he wants to maximize profit in that case, because we are talking about profit in that case, which is the difference between how to maximize the difference between total revenue and total cost. And we obtained the optimality rule in the end that says that in order for the producer to maximize profit, he or she should produce the level of output at which the marginal cost of output is equal to the marginal revenue of output. Of course, in all our lectures throughout the whole course, we assume the existence of a perfectly competitive markets for both inputs and outputs, which means that we assume that we have large numbers of buyers and sellers, easy entry to the industry and exit from the industry, equal access to information, and homogeneous products, which are the characteristics of the industry of agriculture, especially for the producers level, people who are producing at the farm level, whether they are animal producers or agricultural crops. Today, and then remember at the end of chapter 4, which was a very important and difficult chapter, at the end of chapter 4, we identified the supply curve of the producer in that case, in the case of a perfectly competitive market, and we said that the supply curve of the producer is the part of the marginal cost curve from the minimum of average variable cost. This is the supply curve in the short run, and we also identified the supply curve of the individual producers in the long run to be that part of the marginal cost curve from the minimum of average total cost. Okay? I give you lots of exercises. Hopefully, you guys together try to practice doing it. Okay? Today we'll talk about the case of having two variable inputs and producing one output only. Okay? This is the case of having two variable inputs producing one output only. In addition, of course, to a number of fixed inputs, as usual. So this is what is known as it says here, producer decision making, two variable case, okay? Two variable input case, and what the product that should be produced. We call that factor-factor relationship because the inputs are called sometimes the factors of production. Okay? We will talk about the isoquant and the isocost. We will talk about input substitution and obtaining the least cost. And I do not know if in this lecture I will address the product-to-product relationship or not. I don't think I will. I think I will make it in another online lecture. But today we will talk about what is the situation will be if the individual producer is having two variable inputs. Again, it's short-run analysis, producing one output only in addition to a number of fixed inputs. Okay. So here, the production function in that case will look like this: y is equal to a function of x1 and x2. Okay. Here we are having two variable inputs. Okay, before it was y equal function of x1, x2. Given that we have a number of fixed inputs, we still have a number of fixed inputs, but the fixed inputs in our analysis here will not actually have any importance in our economic analysis. So here we are having two variable inputs, and that's why we are saying that y is a function of x1 and x2. Here we will assume that x1 and x2 must be combined together to produce output. Without the combination of x1 and x2, you cannot produce output. Okay? And the most important part here, as it says here, you have to know that you can produce the same level of output by using different combinations of x1 and x2. Okay, let me repeat that. We assume that x1 can substitute x2 and x2 can substitute x1 to some extent. Okay, and that you can produce the same level of output using different combinations of x1 and x2, which means that there is no single method, there is no one single method for producing y, but rather there are more. I can combine, I can mix x1 and x2 in so many different ways to produce the same level of output. Okay, and as a result, we say here resources or inputs can substitute each other in production. Okay, for example, as we said, that usually in economic theory, they assume that x1 and x2 are capital and labor. Okay, of course, we heard before about some, let us say for Egyptian agriculture. In Egyptian agriculture and for usually for the developing economy, or what they call them sometimes the less developed economies, usually more labor is used in production processes compared to capital, because capital is machinery, equipment, and buildings. Capital is man-made inputs, such as tractors, buildings, laboratories, and the like. So in Egyptian agriculture, we say that Egyptian agriculture is characterized as being labor intensive. What does it mean, labor intensive? It means that we are using more labor than capital in our agricultural production practices. If you look at the American agriculture, for example, at the farm level, American agriculture is characterized, and the same thing applies to most economies, most agricultural economies that are developed, they use more capital than labor. So we say that American agriculture and other agricultural practices in developed countries are known as capital intensive agriculture. Capital intensive, it means that we are using more capital than labor. And probably if you compare both, probably we can produce the same level of output whether you are using more labor than capital or more capital than labor, because the reason you are using more labor than capital in Egyptian agriculture because labor is cheap. Okay, the reason actually in the USA they are using more capital than labor in agricultural practices because actually labor is very expensive. But in the end, we can produce the same level of output using different combinations of the inputs that we are applying. As a result, we will define what is known as an isoquant. What is an isoquant? People remember, guys, when I told you that whatever I teach you in economics is always important throughout your life as long as you are studying economics, and there is nothing as such in economics to say that, guys, forget about what we covered before. Okay, there is nothing as such as that, because knowing consumption theory, remember we studied in consumption theory something called an indifference curve. Isoquant is exactly an indifference curve. Okay, but an indifference curve that applies to production theory, that talks about, okay, what are the different combinations of input 1, input x1, and input x2 that can produce the same level of output. Remember, in consumption theory, we were talking about what is the amount of commodity x1 and commodity x2 that I can consume to get me the same level of satisfaction or utility. So it is the same thing here. So isoquants, remember we are talking about consumption production theory. These are the smooth, continuous curve that shows the different combinations of inputs x1 and x2 that can produce the same level of output. And that's why he told you here, recall indifference curve. It means that you remember the indifference curve. And I just explained what that is a moment ago. And it says here, if we are going to talk about x1 and x2 as the two major inputs used in any production processes, any production process, labor and capital could be combined in so many ways to produce the same level of output. Mathematically, the isoquant will look like that. Y bar, why do we call it Y bar? Y bar, we call it Y bar to indicate that we are using x1 and x2, the two variable inputs, to produce the same level of output. Same level of output, it means constant level of output. Because along the isoquant, you obtain the same level of output. Okay, using different combinations of x1 and x2. And that's why the isoquant equation looks like that. Mathematically or graphically, sorry, it looks like that. If you have x1, the first variable input labor, x2 is the second variable input capital. Okay, the isoquant will look exactly like the like the indifference curve with the same characteristics. What are the same characteristics? Number one, never intersects with the vertical axis or the horizontal axis. Okay, convex to the origin, smooth and continuous curve with a negative slope. And the more we move from up here to down here, the slope of the function keeps on declining. It is negative all the way, but it keeps on declining. And the slope of the function, as usual, because remember I am measuring x2 vertically and x1 horizontally, so whether you like it or not, the slope of that isoquant curve is delta x2 divided by delta x1, and it is negative. It tells you that if you want to increase x1 by 1 unit, by how many units you have to decrease x2 in order for you to obtain the same level of output. What is the same level of output that is displayed in that graph here? It is 15 units. So according to that graph, if I use 14 units of x1 and 1 unit of x2, I will produce 15 units of output. If I use 9 units of x1 and the 2 units of x2, I will produce also 15 units of output. If I use 5 units of x1 and the 3 units of x2, I will also produce 15 units of output. If I use 2 units of x1 and the 4 units of x2, I also will produce 15 units of output. Okay? Isoquant, iso it means equal, quant means quantity of production. So any point on that curve shows that you are, as an individual producer, producing the same level of output. Okay, and why the slope is negative here? Because remember, every time when I reduce the level of x1, I must increase the level of x2 if I to produce the same level of output. Because remember, if I use less x1 and use less x2, I will move to a lower isoquant curve that looks like here. And if I use more x1 and more x2 at the same time, I'll move to a higher isoquant here. Lower isoquant here, it means that the level of output is definitely less than 15. Higher isoquant here, it means that the level of output is definitely more than 15. Exactly what we said before about the indifference curve. But here we are talking, rather than we are talking about the two commodities consumed, the x1 and x2, we are talking about the two inputs used, the x1 and x2. And rather than talking about the same level of satisfaction, obtaining the same level of satisfaction along the indifference curve, we are talking about obtaining the same level of production using the two variable inputs. Okay? This is for the isoquant. Isoquant, it means equal amounts of production. Iso means equal, quant, it means quantity of production. Okay. Now, do we have to see the same isoquant that we saw every time? This is what I showed you in the previous graph, but I cannot come back to it according to the video recording. Is the typical one, is the classical one. It is the one that applies to the classical production function. What is the classical production function? The more you increase inputs, output will increase at an increasing rate, output then increases at a decreasing rate, output reaches the maximum, output decline. And as a result, you will have that type of production function. That type of an isoquant. Okay? But here, remember, when you talk about the relationship between x1 and x2, capital and labor, for example, sometimes you can have complete substitution between x1 and x2. Sometimes you can have partial substitution between x1 and x2. Sometimes you have to use certain amount of x1 that goes with certain amount of x2 in order to be able to produce to start with. Okay, and these are the types of, or the different shapes of the isoquants that we will address here. It all depends on how much x1 can substitute x2 and how much x2 can substitute x1. Why do every time I say how much x1 can substitute x2? Because I am measuring x1 horizontally and x2 vertically, and as a result, x2 in that mathematically x2 is a function of x1. Okay, which means that when the level of x1 changes, the level of x2 will change accordingly. And that's why the slope of the isoquant is delta x2 divided by delta x1 to tell you, and it is negative to tell you by how much you are willing, by how many units you are willing to sacrifice x2 if you want to increase the level of x1 by 1 unit. So in the first case, we have what is called the perfect substitutes. It means that x1 and x2 can substitute each other perfectly. Okay? And it is a reminder here, don't confuse yourself, it is a reminder here of consumption theory. Okay? Perfect complements, it means that in order for you to produce at all, you have to use some X1 and some X2. Okay, here you are using what we call it, you have to use X1 and X2 in perfect proportions. Okay, imperfect substitutes, this is of X1 and X2, this is the case that you saw in the previous slide, which means that you have to use some X1 and some X2. You cannot use X1 only to produce, you cannot use X2 only to produce, you have to use a combination of X1 and X2 no matter what this combination is to produce the same level of output. And these are explained on that we have here. This is the case of perfect substitutes right here. In perfect substitutes, here I have X1 is the first variable input, X2 is the second variable input, and the isoquant in that case will look like this. This is the isoquant. Okay? Let us say y equal 15. Okay? Here I can tell you that because X1 and X2 are perfect substitutes, I can use X1 only in production to produce the 15 units of output. Or I can use X2 only in production without using any X1, I can still produce 15 units of output. Or I can use any combination between X1 and X2. Okay? This case is rare. This case of an isoquant is rare, but sometimes you can have it in some industrial processes. Okay? The common one, as I told you, is right here. Okay? In order to produce the same level of output, which is the isoquant that we have, you have to use some X1 and X2. How much X1 and X2 that you can use? Can you use a lot of X1 and a little of X2? Yes, you can. Can you use a lot of X2 and a little of X1? Yes, you can. Okay? But you have to use some X1 and some X2. So the X1 and X2 substitute for each other, but not perfectly. Okay? But rather imperfectly. And this is the case in the middle of the perfect complements. Here they tell you what? X1 is the first variable input, X2 is the second variable input. And the isoquant is the red thing that you see right here. Okay? This is also what you see here is the isoquant. Okay? The red isoquant looks like that, very odd. It looks very strange, it looks very bizarre. To tell you that you have to use this amount of X1 and this amount of X2 in fixed proportions if you are to produce at all. Okay? This is what the imperfect complements they tell you. And sometimes you can have a relation like that in agriculture. But again, the most common type of isoquant without going into great details is this one to the C, which is imperfect substitutes X1 and X2. Now, what is the slope as usual? Remember, when we studied indifference curves, we talked about the slope of the indifference curve. Okay? Marginal rate of substitution curve. Here we have the same name. But usually they call the slope, because we are talking about production theory, and in order for the economists to distinguish between production theory and the consumption theory, they called that slope of the isoquant, they call it the marginal rate of technical substitution. Okay, MRTS. But if you call it marginal rate of substitution, is also correct. Okay, so here the marginal substitution between X1 and X2, okay, it means how many units of X2 you are willing to sacrifice in order to increase the level of X1 by 1 unit. And as usual, it is equal to delta X2 divided by delta X1, or what happens to X2 when X1 changes by 1 unit. If X1 goes up by 1 unit, X2 must go down by some units. If X1 goes down by 1 unit, X2 must go up by some units, because the slope is negative. Because if you use more X1 and more X2, you will move to a higher isoquant. Remember, we are talking about relationship along the same isoquant. This is the slope, remember. MRTS is the slope of the isoquant. Okay, and the sign must be negative because along the isoquant, as long as you are talking about one isoquant, then the level of output is constant, and in order for you to achieve constant level of output or same level of output, in order for you to increase X1, X2 must go down by some units. Okay? And this is exactly tell you that it is diminishing. What does it mean diminishing? It means that if you measure the slope of the isoquant right here, remember if I take a tangent here, and if I measure the slope right here, if I take a tangent here, which one is more sloped? If you are standing here, are you going to fall faster, or if you are standing here? Definitely up. So we say that the slope of the isoquant at point A is bigger than the slope of the isoquant at point E. But remember, and as we move from point A to point F, despite that we are producing the same level of output using the inputs x1 and x2, the slope keeps on declining. Remember, it is declining and negative. So if the slope at point A, for example, is -5, over here at point F or at point E is -1. And we say that -5 is bigger than -1. Hopefully this is clear. And this is how you measure the slope, remember. You take the slope of the tangent, and the slope is always delta x2 divided by delta x1. Hopefully this is clear. And this is the same thing that we said in consumption theory, by the way. It says here, when we decrease x2, output drops. Okay, forget about this one. Forget about this slide. This is hocus pocus for the same, that says the same thing, and I would rather show it to you on the board. Okay, and I showed that to you, by the way, in consumption theory. But just forget about it. What you need to get out of this slide in order not to confuse you and make you really sweat, because in order for me to explain the meaning of when we decrease x2, output will drop by the amount of decrease in x2 multiplied by its marginal physical product, and then if we increase x1, output will increase by the amount of increase in x1 multiplied by its marginal physical product, which means that along the isoquant, because there is no change in the level of output, the drop in x2 multiplied by the marginal physical product of x2 must be equal to the increase in x1 multiplied by its marginal physical product. And as a result, the conclusion here will be marginal rate of technical substitution between x1 and x2 is minus delta x2 divided by delta x1, or minus MEPP x1 divided by MEPP x2, without knowing these details, because I would rather convince you in a class showing you that relationship. But please believe me for now, without going into details and without bothering you by that, please remember that the marginal rate of substitution between x1 and x2, which is the slope of the isoquant, is either delta x2 divided by delta x1 and it is negative, or MEPP x1 divided by MEPP x2. Remember, in my story here, this is very, very, very important. I am measuring x1 all the time horizontally and x2 all the time vertically. Okay, if you measure x2 horizontally and x1 vertically, then the slope of the isoquant will be delta x1 divided by delta x2. So please bear in mind that usually in most economic textbooks and in these slides, we always measure whatever is denoted by a subscript 1 to be measured horizontally, and whatever is denoted by subscript 2 is always measured vertically. Now we are going to identify something called the isocost line. Isocost line, again, is synonymous to the budget line in the production theory. Okay, the isocost line is synonymous to the budget line. Okay, but isocost line, that's in the case of production, and the budget line is in the case of the consumption. What is the isocost line? The isocost line is a line, okay, that shows the different combinations that the individual producer can use, and that can cost the producer the same amount of money. Okay, again, iso, it means equal. Isocost, it means that the cost is the same. Okay, and it is definitely measured in dollars or in monetary units. Isocost line is all combinations of inputs x1 and x2 that cost the producer the same amount of money. And here it says, doesn't that remind you of the budget line? Okay, here we have the iso equation of the isocost line. Here they tell you that the C bar, why C bar? C is cost. Bar, it means constant. Okay, so here we have constant cost. It means the same cost is equal to unit price of the first variable input, which is P of x1, multiplied by the amount used of the first variable input, plus P of x2, which is the unit price of the second variable input, multiplied by the amount used of x2, which is x2. Okay, which is the same as budget line, believe me. The whole idea here is that rather than calling x1 and x2 two commodities consumed, we are calling x1 and x2 two inputs used in production. And rather than putting here on the left hand side, putting budget or income, what we call it capital I, we are putting cost. Okay, again, you are looking at the same coin but from different perspectives. If you look at the coin from the right, it is consumption. If you look at the coin from the left, it is production. And this is how, like any straight line. It is a line. It has constant slope. We are measuring again x1 horizontally, x2 vertically, and that line must come from here to here. Why it must come from here to here? Why it must come from the axis? It cannot fly in the air. Okay. Remember, how do we graph it? Suppose that the level of cost is $50, and suppose that the unit price of output is $5 a unit, and the unit price of the unit price of the first input is $5 a unit, and the unit price of the second input is $2.5 a unit. Forget about AED. This is dollars. Okay. In that case, how do we graph it? Okay. You go to the equation in the previous slide, and you say that when x1 equal to 0, what will be the value of x2? And then you get it here. This will be the 20. When x2 is equal to 0, what is the value of x1? You get 10. Connect, this will be the slope. What is the slope of that line? It is delta x2. Sorry, it is the tan of this angle. Tan of this angle. Let me put it here in red. Tan of this angle. Let me put it here in writing. Tan of this angle, which is this part divided by this part. What is this part? Okay, right here, what is this point right here? This point right here is C bar divided by Px2. What is this point right here? It is C bar divided by Px1. So when you divide C bar divided by Px2 by C bar divided by Px1, you will see that the slope of the iso cost line is P of x1 divided by P of x2. P of x1 divided by, just to go home and practice graphing that curve here. And what you will get in the end is that the slope of this iso cost line is always, as long as you are measuring x1 horizontally and x2 vertically, is always P of x1 divided by P of x2. P of x1 divided by, just do it at home and you will find it like that. The slope of this iso cost line is always, which means that the slope of that iso cost line, what is P of x1? 5. What is P of x2? Is 2.5. Okay? Divide 5 by 2.5. This will be the slope, and it is again negative. Why negative? Because in order for the individual producer to pay the same amount of cost, which is $50 in that case, if I to increase x1, I have to decrease x2. And if I to decrease x1, I have to increase x2 in order for me to pay the same amount of money. Because if I increased both x1 and x2, I have to pay more money, and as a result, the iso cost line will be like that. If I reduce the amount of x1 and x2, then I will pay less money, and the iso cost line will be like this. But remember, we are talking about iso cost line. Iso cost line, it means that the cost that the producer will pay will be identical. Look at the blue line here. Look at all these yellow dots here. This yellow dots shows different combinations here. For example, 9x1 that goes with 2x2. If I do that, it will cost the producer the same amount of money, which is $50. Look at right here. If I use 3x1 and 14x2, it will cost the producer the same amount of money, which is 15, and the same thing applies to any point along that iso cost curve. And this is the slope, as I told you, it is Px1 divided by P of x2. And it is negative. Now we introduced the iso quant and the iso cost line. Now what is the moral of the story? What do we want to obtain in the end? I want, as an individual producer, to know the optimality condition that will allow me as an individual producer to pay the least amount of money when I produce a given level of output. I want to be efficient, remember, and efficiency is what we look for in economics. So I want to know how much of x1 and how much of x2 I should use, okay, to minimize my cost, the amount of money that I pay for x1 and x2, when I produce a given level of output. Remember, not the maximum level of output. So here we talk about this. What is the least cost of inputs to produce a given level of output? Remember, least or minimum must go with given, which is constant. Least cost cannot go with maximum output. It cannot. It doesn't make sense. It is impossible. Or what is the maximum output that could be produced with a given cost? Remember here, if I talk about maximum output, then you have to talk about given cost. Okay? If you want to talk about least cost, then it has to go with given output or constant output. Okay? And the result, as I told you before, remember guys, if you remember consumption theory, we as sheikh or priest, I consummated a marriage between, remember in consumption theory, between the budget line and the indifference curve. Here I'm going to consummate a marriage between the isoquant curve and the isocost line. And optimality will happen when the isocost line is tangent to the isoquant. Okay? At the point of tangency, the slope of the isocost line will be equal to the slope of the isoquant, which means that if you as an individual producer wants to produce a given level of output using the least cost of inputs, then you should use the amount of x1 and x2 where the slope of the isoquant is equal to the slope of the isocost line, which means that the slope of the isoquant is either delta x2 divided by delta x1 or MPP x1 divided by MPP x2 must be equal to P of x1 divided by P x2, which is the price ratio between the two inputs used. Okay? And here it says we wanted to produce 20 units of output. This is the constant level of output. Okay? What is the best or the least cost combinations of x1 that I should use in the graph? Point A, as you will see later on, it is the best, it is the equilibrium point. Okay? As you can see here, this is the point where the isocost line is tangent to the isoquant. So in that case, if I want to produce 20 units of output and the paying as an individual producer the least amount of cost, I should use 5.5 units of x1 and somewhere like 9 units of x2, because here the graph is not that accurate. Okay? This is again assuming that the unit price of x1 is $5 a unit and the unit price of x2 is $2.5 a unit, and the amount of money that I'm going to be paying, which is the equal amount of money I'm going to be paying, or the equal cost or the isocost, is equal to $50. In that case, if I use that much of x1, which is somewhere between 5 and 6 units, and use somewhere between 8 and 10 units of x2, okay, I will produce 20 units of output, the least cost possible. Okay, and this is the optimality condition. In that case, we call point A, which is the tangency point, the point of equilibrium. And this is the equilibrium. The slope of the isocost line and the slope of the isoquant must be equal. And this is the condition here. Here, remember, this is marginal rate of substitution of x1 for x2. They call that, by the way, marginal rate of technical substitution of x1 for x2. It is equal to minus delta x2 divided by delta x1, or minus MPP x1 divided by MPP x2. Okay? So the condition tells you that delta x2 divided by delta x1, okay, this is the condition, must be equal to the price ratio, px1 divided by px2. Okay? Or replace delta x2 divided by delta x1 with MPP x1 divided by MPP x2. It is the same thing. Must be equal to the price ratio. This is the optimality condition. Or you can write it that way if you like. MPP of x1 divided by its own price is equal to MPP of x2 divided by its own price. All that is the same. Now, suppose that, as usual, we do comparative static analysis. Okay? Now, remember, I have to give you in any problem, I have to give you the unit price of x1, I have to give you the unit price of x2, and I have to tell you the amount of cost that, or the amount of money that the individual producer has in his or her pocket. I have to give you that. Now, I can make different scenarios. I can change P of x1 only, everything else remains the same. I can change P of x2 only, everything else remains the same. I can change the amount of cost, everything else remains the same. Okay? And in that case, it is the same that we studied in consumption theory. Suppose that, for example, rather than having in my pocket $50, but I have 70, what will be the shape of the isocost, the new isocost line? It will be right here. Suppose that rather than having 70, I have 30, which is less than 50. Then the isocost line will be like here. Okay? And then suppose that this is the case of a change in the amount of money in the pocket of the producer, which is C. I gave you 3 different C bars. Now, suppose that Px1 changes, what will happen to the isocost line? Remember, the word rotate. The isocost line will rotate around x1. Suppose that I changed the price of input x2, which is I changed Px2, then the new isocost line will rotate around the vertical axis, which measures x2, exactly like we covered before. So you can make the following scenarios. Changing C, everything else remains the same, and the changing C, it means that you increase C or you decrease C, so you have two cases. Changing P of x1, everything else remains the same, or ceteris paribus, which means that P of x1 can go up or it can go down, so you have two other cases. And then for Px2, you can either increase Px2 or decrease Px2, you have two other cases, so a total of 6 cases or 6 scenarios that you can make, and you can show that graphically. In all scenarios, the optimality condition is the same. Use the amount of x1 and x2 at which the slope of the isoquant is equal to the slope of the isocost line if you want to minimize your costs of production while producing the same level of output. And this is the end of our lecture for now. Hopefully it was of benefit. See you. It doesn't have, by the way, this part doesn't have a corresponding part in Shireen Word documents. It doesn't have any corresponding part. Why? Because it is easy. Sometimes I think I put a document called more on isoquants and isocost line, but actually there is nothing much in that, because what I said here is enough for you at your level to understand. This is the case of having two variable inputs producing one output only, in addition to a number of fixed inputs which we ignored in our discussion here because they are there anyway and they have no value or no significance in coming up with the optimality condition in this case, which is the case of having two variable inputs producing one output. See you inshallah in our next class. Bye bye.